There are really big numbers and really small numbers too. And what we need to understand is that we can write these numbers without all the place values if we don't want to. It's called scientific notation. Did you know that there's roughly 321 million people in America? And that means if they all stood shoulder to shoulder, we could wrap around the earth 7 times. That's a true fact. It's crazy, isn't it? So what we need to do with a number like this that's really big is we don't want to have to write all the place values. Now let's understand what a place value is. Each place value means that we're multiplying a number by 10. So if we remove place values, that means we got to have like a storage place to put these place values so that if we ever want to make this number look like it does right now as 321 million, we can do it. So let's count how many place values we actually have. 1, 2, 3, 4, 5, 6, 7, 8. There's 9 total place values. Now, if you've watched any of my other tutorials about scientific notation, we know that we have to have a number in scientific notated form that's 1 or bigger and that's smaller than 10. So how can we take a number like 321 million and shrink it down? Well, what I'm going to do is I'm going to make this look like $3.21 by putting a decimal between the 3 and the 2. And now all I need to do is figure out, I've written my significant digits of 2 and 1, and I've got to figure out how many place values did I shrink this number, because we got to put those in storage, right? We've got to make sure that we show that this number has the place values, but we're not showing all of them. When we multiply by 10, the exponent is where we store those place values. And every time we multiply by 10, we're able to increase our number by 1 place value, make it bigger. So if I was going to turn $3.21, the way that this number looks, into 321 million, I would need 1, 2, and then 3 more here, 3 more here. So that gives me a total of 3, 6, 7, 8. 8 place values that I'm storing to use at a later date if I want to make my number a much bigger. And this is now in scientific notated form. My number falls between 1 and 9.99. And I've got 8 place values stored if I want to use them to make the number look like it originally did of 321 million. All right. Well, we started with a big number. Now, let's start with a smaller one. If we look at a small number, something that we may see in science class, we look in microscopes all the time at very, very tiny objects. Let's say that this thing was 0.0000145 centimeters. How can we write this without having to write all the zeros? Well, we can write it in scientific notated form. Let's follow our rules once again. We got to make sure that our number looks like it's between $1 and $9.99. So how am I going to do that? Well, I'm going to put the decimal between the 1 and the 4, so it looks like $1.45. I don't want to put it between the 4 and the 5 because that would be $14.50. I don't want to put it after the 5 because that would be $145. And I don't want to put it between the 0 and the 1. That'd look like 14.5 cents. We've got to make sure it falls between that $1 and $9.99 range. Okay, how many place values am I actually making this number appear bigger? Yeah, we're actually making it bigger. We're going from a very small decimal number to $1.45. We're making it much bigger this time. So, if I put down 1.45, we're still going to have place values, but we're going to store them a little differently. So So here's where I'm going to store my place values. What is going to be the exponent that I put here into storage? Well, if I look where the decimal used to be and where I now have it, I have 1, 2, 3, 4. I've got 5 place values that I made this number appear bigger. And if I was going to go the opposite way, I have $1.45 and I want to go the opposite way, I'm going to actually make it smaller. So that means I'm going to have a negative amount of place values that I want to put into this number. We're going to go and make a number smaller by using negative exponents. So we have our answer in scientific notated form. 1.45 times 10 to the negative 5th. That's the same thing as what we started with, which was 0. And here's our 5 place values, 0, 0, 0, 0, 1, and then the 4 and the 5.